Hello everyone, this is DSS Zindabad. Let's talk about the daily challenge for today on code. So the problem given to us is largest divisible subset. Let's jump into the problem statement. Given a set of distinct positive integers nums, we need to return the largest subset answer such that every pair, that means answer I comma answer j of the elements in the subset satisfies this condition. That means if you take the modulo of the two elements, right, they will be equal to 0. That means they're multiple of each other. Okay. So if there are multiple solutions, we can return n. So basically, this problem statement is saying that you will be given something like a vector nums. It will have different values, right? Suppose these are the different values that this vector has. So what I have to do is from this vector, I need to figure out the largest subset, right? Now, basically, when you talk about a subset, it is not continuous in form. So that means you can skip certain elements. So what I need to do is I need to find the largest subset. Now, how I need to figure it out? It needs to satisfy a particular condition. That is that one element, for example, there were just two elements in my vector, or we can say in the largest subset I was creating, right? So if I take a modulo, I'll get a 0, right? So that means that these are multiples of one another and I need to return the largest possible subset. I hope the problem is clear, right? So now let's talk about its approach. Considering this example, what I can see is that, see, for me to figure out at any point of time which will be the largest subset, I need to know that what all elements can come together, right? So what all elements can come together. So that means I should know the multiples for each element in the array. Okay. So when we do that, I need to make a choice. That means if I am constructing a subset which will satisfy the above condition, right? And figuring out the multiples, I need to make a choice. Now, how do I need to make a choice? The choice will be at any point of time, should this element be added into the subset or not? So I'll have two choices. That is, you can either take the element or you can not take the element. Sounds familiar? Yes, it is recursion. Now, alongside this, the first step that you need to take care of is before making these choices, you need to sort the given array. Now, why do we need to sort the given array? It is because, see, when you will be making these choices, the end goal is to find the multiple of a particular number, right? So what happens is each time when you're making this choice, it will be dependent on a condition, right? And that condition says that you need to use a previous element so that you can keep a track of what all is added into your subset. For example, let us suppose I had something like 1, 2, 4, and I'm standing on 8. Now, for me to know that does this 8 also is also multiple of this subset which has been created, I need to know the previous one. It is easiest to know the previous one, right? So you will be maintaining the previous. Now, why does it need to be sorted is because suppose I had something like, it was not sorted. I had 4, 2, 1, and here I was standing on the third index. I had to figure out this element that has a value 3. Now, if 1 is the previous in this case, you see 1 modulo 3 will give you 0. But if you will say 4 modulo 3, that will not give you 0, right? So that is why we need to sort the given array. I hope it is clear. I'll quickly write down the approach. The first step is to sort the given array. As soon as you've sorted the given array, the second step that you will be doing is you will say, I have to use recursion, right? Wherein I'll have two choices, to take or to not take. And while I am figuring out these choices, I'll be maintaining a previous element for understanding that does the particular element I'm standing on belongs to this group or not. Okay, so I can say to check the belongingness for an element to a group, and this belongingness basically depends upon is this element a multiple of the subset or not. Okay, I hope the approach is clear to you. Let's quickly code this up and then we'll talk about its time and space complexity. Okay, so this is the problem statement. So what I'll do is I'll quickly first say let's sort the given vector that has been given to me, right? So we'll use the STL function and after that, okay. So once we have sorted the given array, right, which was our step one. So after sorting, what I need to do is I need to use recursion, right? So for that purpose, what I'll do is I'll create a function, right? Let's call it solve. We'll pass in the current nums vector that has been given to us. I'll pass in the current index we're standing on. Let us assume we're standing on the 0th index, right? Now, as I told you, we have to take care for previous. So in this case, I'll pass previous as 1. And now, as you can see, final answer that needs to be returned should be of type vector int. So you can have something as vector int, supposedly, let's call it temp, right? And I'm passing my temp here. Now you might ask that why have we used 1 here in the case of previous. So we have taken previous is equals to 1 because according to mathematics, 1 is a multiple of for every number. Okay. So this has been done because 1 is the multiple for every number in the number system. Okay. So now as I have done this, I need to finally return an answer. So what I can do is I can have something as, see, every time this temp is going to be updated, this will be holding my subset value. That means the largest subset recursion could find. So it needs a comparison, right? So for that, let's simply create a vector int answer, right? It's a global vector and we'll be making comparison with this vector, right? And I'll return answer eventually. Return answer. Now let's quickly create the solve function. As you know that here we are basically forming something, we're adding or subtracting something from a vector. So the function will be of void type solve, right? I'll quickly copy paste this part here. Then we have the index and then we have the previous and the vector that we have created, that is passed by reference. Yeah. So now let's quickly write the code. See, whenever you're writing recursion, recursion is divided into 3 parts. First one being the base condition, then the recursive call, and then exploring all the possible things you can do on that recursion, right? So for the time being, let's leave the base condition as it is. We'll write it later. What I'll do is I'll quickly jump onto the take and not take part. So basically, if at any point of time I have to take something, that means I have to take that element into my subset. So how will I do that? I can do that if I check this one condition. I say if nums of index and if you take a modulus with the previous, that means they are a multiple. In that case, what you can do is you can push this element into the temp, which is maintaining the current possible subset which satisfies the following condition. So this will be nums I, right? Else once you've done this, you'll go to the next element. So you'll say solve, right? And you just pass nums. Index will be incremented because we started from 0. Previous will get changed. Now previous will be what we were currently standing on, that is nums I, and temp is also passed. After that, once this call is completed, right, we've reached the very end. After that, what we'll do is, as discussed, we'll pop this element. We'll say, suppose this element was not taken there, right? So after this, we'll go to the not take condition wherein I'll quickly copy paste this only. Here, the previous will not be changed. So though we are incrementing by one index, the previous remains the same. Why? Because it is a not take condition. Okay. So now, as we've written the recursive code of take and not take, now let's talk about the base condition. See, basically, you'll reach the base condition only when at any point of time your index becomes greater than what is the size of the given vector, that is nums dot size. If this happens, what you can do is you can simply compare that is the current temp which you were building, which was storing the possible largest subset which satisfies this condition, that is its size greater than what is the size of the global vector that we've created that will finally return. And if that is the case, you simply say that answer is equals to 10 and you return. Okay, I think we're good to go. Let's quickly run and check once. Okay, yeah, because we have used index here. So let's write index quickly. I think we're good to go. And it is running fine. This was the example that we taken, right? If we submit it, we'll get a TLE. So let's quickly submit it and see. It is taking some time. Yeah, and see we got a TLE. That is because the present code has a time complexity which is exponential in nature. Now let's quickly copy paste this code, have a dry run, discuss its time and space complexity and how we can optimize it. So basically, this was the code that we were working on, right? And we know that this has a time complexity issue. So let us have a dry run and understand how can we possibly have an optimization for it. So let us assume the nums array that was given to me was 2, 1, 3, 5, 6, 4, and 7, right? So this is what I have right now, 0, 1, 2, 3, 4, 5, 6, 7 elements. So I'll start from here. First, this will get sorted. So I'll have 1, 2, 3, 4, 5, 6, 7. I have these elements in the sorted order. Once I have sorted them, I'll create a vector in temp and I'll call the first function. So I'll be creating both the recursion stack space as well as the recursion tree for you to understand. So basically I have 0, 1. 0 is the index and 1 is the previous, right? So the base condition is not satisfied because the size of nums is 7, right? So as index is 0, it is not satisfied. So we'll come to these if condition. So you're standing here on the 0th index. You will say, is 1 divisible by 1? Is it giving 0? That means, are they multiple? You say yes. So you'll push that in temp. So now your temp has 1. And now you'll call the solve function. Solve, index gets incremented, index becomes 1. Now previous is what was nums index. Nums index was 1, right? So this is the other call that has been made. So basically you had S01 initially. Now S11 is added into your recursion stack space. Once you come here, you'll check for the if condition. Index is 1 and the size of the nums vector is 7, not satisfied. You go in this condition, you are standing on 2. Now you will check, is 2 divisible by the previous is 1 and the answer is true. So you'll add it into temp. Right now 2 is added, another function call is made. Now I becomes 2, previous as it is standing here will become 2 and this call is added. So you have 2 comma 2 in the recursion stack space. So when you are standing here on 2 comma 2, what happens next is, that means you'll see as the index is 2, it is less than 7, not satisfied, you come here, you will say nums index. So on 2 you get a 3. As you get a 3, you will say is 3 a multiple of 2? And the answer is false. So you'll not go in this if condition, you'll come directly here, and now this call is made as the previous is not incremented, right? That means the previous is not changed, only the index is incremented. So you have 3 comma 2. So now you go to the third index. The condition is still not satisfied. You come here, you are standing on the third index, that means on 4. So you will say, is 4 a divisible of the previous? Previous was 2. If it is, it says yes. You will say add that into the 10. Once you did that, you will have another recursion call. I'll quickly zoom out a little, right? You will have another recursion call that will be S, and now your index will be 4 and your previous will also be 4. So now your recursion stack space has, as earlier, it had S 3 comma 2, right? After this, now it will have S 4 comma 4, and you're standing here. Now, as you can see, 4 is less than 7 if condition is not satisfied. The standing on the fourth index, you get a 5. So you'll say, is 5 a multiple of 4? And the answer is no. You will not go inside this if loop. You will come here. So S, you'll go to the fifth index and the previous remains the same, 4. As you go to the fifth index, you get a 6. You will say, is 6 a multiple of 4? Answer is no. So what happens is, these all are added into the recursion stack space. So here you have S 5 comma 4, and on the top you have something like S 6 comma 4. Now what happens is, as this if condition was not satisfied, you will come here and you, as I told you, this function call will be made. You will check the sixth index, that is 7, and as 7, see, this if condition is not satisfied yet. Why? Because I is 6 and we need it to be at least greater than or equal to 7 for it to be satisfied. You come in this if condition, this is also not satisfied because 7 is not a divisible of previous. Previous was 4. So this is not happening. Another solve call is made. Now, here you will see you get index 7 and the previous remains the same. As soon as you get this, right, now is this is being satisfied. So you are standing here. Now this is satisfied. Why? Because index is equal to the num size. So in this case, you will compare and see answer had a size 0, temp had a size 3. So you will say answer initially has my answer, right? So answer is equal to 3, right? So here, now as we've made this, this becomes the answer, right? So now my answer has this value and you can simply return it. So that means you will return back here. And once you return back here, as in 6 comma 4, right, you were here only. So it has completed its life cycle. It will return back. Similarly, this will return back. As soon as you are standing on 4 comma 4, right? Because in the case of 4 comma 4, you were standing here when the function call was made. Now you will pop back the element that has been added. That means you'll subtract 4 from here. That you'll say that 4 is not a part, right? And once you are done with it, you will make another call. So here the call will be going to the fourth index, right? And the previous remains the same. So previous was 2. So now again another tree of recursion will be developed from here. Now what happens is, I'll say that okay, as I'm standing here on the fourth index and my previous is 2. So I'll say on the fourth index I have a 5. I'll check is 5 divisible by 2. I get no as an answer. And my temp is currently 1 comma 2, right? So after that, another, if as this is not satisfied, you will go to the other condition. So this is says increment the index becomes 5 and previous remains 2. On fifth, you get a 6. So 6 is a multiple of 2. So now it gets added. So now temp will have 1, 2, and 6, right? And another call will be made from here. You will go to S 6 comma and the current element that you had was 6 as the previous. So now as you're standing here, right, you will check that is the element. That means it's 7 divided by previous, that was 6, and the answer is no. So you'll simply skip the if part. You'll go S, you'll go and say S, move the index, previous remains the same. Now again you have reached 7 and this satisfies the base condition. It will check for this value, but as you can see that temp has a value 3, so does answer. So basically this does not get updated, you simply return and this tree will be created. So from this tree, what you can see is for every element, you have a choice. And that choice comprises of two things. So you have two choices. You can not take it or you can take it. So because of that, the time complexity becomes exponential in nature, right? So that is big O of 2 raised to the power n. And similarly, the space complexity is O of n. Why? Because at every point of time, a recursion stack space is being formed. And in the worst case, we can assume all the elements are there in the recursion stack space. Now, whenever we have such problems, what we do is we'll use something as DP. Now, why am I saying that we'll be using dynamic programming is because if you will draw a tree, a recursive tree for the above question with a smaller vector, you will be able to see overlapping subproblems, right? So whenever you have overlapping subproblems, you can use something as DP. Okay. So what happens in DP is it says that once you have figured out a certain answer, you will not recompute it. You just simply store it in one place. And once you need it, use it from here rather than recomputing it from the code of lines. Now let's quickly make the changes in the DP, right? That is simply by adding a DP vector, which is known as memoization. Nothing new is being done. Only a vector will be added and the TLE error will be resolved. Okay. Now let's jump into the code space. Okay. So this was the code that we've written so far. What I'll do is I'll quickly create a DP vector, right? And it will be a 1D DP, right? So basically, I'll have something like int n nums dot size, right? N, and I'll initialize it with -1. I'll pass it to my solve function. Here we have the DP passed as a reference, right? Now, basically what you need to know is this DP here that we are using, right? I'll quickly write it here. That this DP vector, it is basically stored to store the length of the longest divisible subset ending at that index. Okay. So it is to store the longest divisible subset at that index. Okay. So now what happens here is as we have this base condition, right? This base condition will remain as it is, will not change anything. We'll make a minor change here, right? Where we were checking this nums condition, we'll check alongside this, we'll add an and condition. We'll say that if the temp dot size is less than DP's index, right? If this is the case, then what you will do is you will say DPI. That means that DP index should store whatever is the size of that subset that we are potentially considering to be the longest subset answer. Okay, then you will push it, you will call the solve function, and this code remains as it is. Now let's quickly run and check if it's working fine. I think it should. Okay, yeah. Basically, we did not pass DP in the solve function calls that we are making later. Let's quickly add that. I think we're good to go now. And yeah, it's working fine. Let's submit it. So yeah, it is working fine. Now let's discuss its time and space complexity. So basically what is happening here is I'm using a DP vector, right? And that DP vector is basically, it is used to memoize the length of the longest divisible subset ending at the index I. Okay. And while I'm using this, now my time complexity has boiled down to linear. And my space complexity is also of n because I'm using an extra DP vector, right? Nothing has changed, only we've added DP. This is known as memoization. Okay, I hope this is clear. You can quickly have a dry run, right? Basically, this DP vector at each point of time will be storing nothing but the size of the potential subset till index I, right? So it is really easy. You can have a dry run. If there's any problem, you can always comment and we can discuss it. Thank you so much for watching the video. Please like, share, and subscribe.